post-lunch. We're going to have a rousing speaker with a really provocative theme of the future of AI for maths. And as Ursula mentioned, Mateja actually spoke at the first Big Proof event. And so it's great to have the kind of part two of this saga presented to us. So Mateja will speak, and then we'll have a good discussion, I think, following this.
Okay. Thank you very much. Thank you for having me. Today, we're going to be exploring a frontier where AI isn't just solving maths. It's redefining how we are discovering it. Imagine a world where machines don't just compute answers, but propose questions that we may have not thought of before, where AI is a mathematician's partner. And this isn't science fiction. Let me show you how close we are. Mathematics is the bedrock of scientific discovery, yet formalizing and discovering new theorems remains painfully slow. And if anything, the first two talks we've heard today confirm that. But now AI offers us a paradigm shift. Take an AI reasoner like DeepMind's Alpha Proof. It solved a math Olympiad problem that stumped most humans using 100 million formalized theorems. The news headlines position these intelligent systems' victory as a glimpse of an AI as a collaborator. AI offers the ability to automate, to accelerate, and even collaborate in mathematical discovery. Today, we'll unpack how this collaboration works and why it matters to all of us. And Tim, you might recognize your own words in there. So the question is, why is this shift happening now? So let's connect the dots. Three transformative shifts are converging. First, we have the explosion of large language models like ChatGPT that can now pass informal human math and generate code. Second, AI proving systems like DeepSeek do neural reasoning that can now solve Olympiad problems. Third, formal tools like Lean4 let us verify proofs at scale. So together, they're creating a perfect storm. We have computation, we have data, and we have interest. So we now have an opportunity to go beyond automation to discovery. But my own journey here began with something far, far simpler. Let me share a story. I always loved maths, and for the intuition that it elucidates, for the beauty and the elegance of the solutions that it can capture. And here's one such intuitive solution to adding up natural numbers that I learned in primary school, and that my kids are learning about it at school now. And you may remember this theorem and perhaps even the visual solution from your maths classes. So I wanted to capture this kind of reasoning on machines, and years later, I built a theorem prover that could do exactly this visual proof and also verify that it's correct. Today, AI reasoners are capable of much more complex reasoning, and I never imagined then that machines could invent math. And that curiosity led me to here. And now in my work, I ask questions like, can we create machines that can generate novel, high-quality conjectures? Can these machines validate human proofs? And can we capture human intuition and create AI systems that collaborate with humans in order to advance discovery? Let's hear your take on these biggest challenges. So let me do a little poll by show of hands. So what do you think is the biggest challenge for advancing AI-driven mathematical discovery? So is it integrating a human collaboration, creativity, and trust? Is it validating proofs rigorously and efficiently? Or is it generating novel, high-quality conjectures? So let me see, who thinks A? Okay. Who thinks B? Oh, lots more. Okay. And who thinks C? Oh, a lot. Okay, interesting. So here's a twist. Our work tackles all three. Here's how. So imagine an infinite loop, and AI generate the conjectures here. And then we validate them with a neural prover, right? And then we learn from human feedback to generate new conjectures. So, for example, what if our system proposed a conjecture, a human added one condition, or perhaps suggested a fix, and suddenly we have a publishable theorem? This is our vision. This is collaborative discovery, the way we see it. This is a gate to infinite mathematics. I'll keep returning to this loop, to our vision throughout the talk. But how close are we? Let's break it down. So think of this as a puzzle. For the first collaboration piece, we investigated in our empirical study what AI reasoners are good at and what they're bad at when they're collaborating with human mathematicians, and how actually mathematicians, in fact, trust them. Rigor and validity, we've solved a part of this via methods that we built, like auto-formalization, which can formalize millions of theorems and therefore scales data for AI using large language models, and with tools that bridge informal and formal maths that's now able to solve Olympiad problems. And conjectures, we are now building a conjecturer that is progressively generating better conjectures. But these are only the first steps towards human AI collaborative discovery. The full picture needs, first of all, each of these pieces completing, and most importantly, all three need interlocking and supporting this cycle to have a chance at AI-human collaborative discovery. Remember how I told you earlier that I've always loved maths and that I want to make AI machines our true collaborators? Well, let's start with collaboration. With the proliferation of ever more powerful large language models, I wondered, would mathematicians use such AI reasoners to explore maths and help them solve new problems and gain new insights? Would you use such an AI mathematician yourself? Maybe. I hope to persuade you should. So we decided to carry out an empirical study with real mathematicians, some of them seriously good experts. At least 2 of them are sitting in this room. Thank you very much for being our participants in this study. And here is what we did. We designed a human-AI interaction environment called Checkmate for doing maths. We wanted to see how well LLMs can reason about maths in a collaborative way. We were particularly interested in this interactive element and how this interaction between a mathematician and an LLM evolves as the collaboration progresses. So our environment looks like this, and a mathematician can chat with the system and prompt it to explore deeper with the hope that LLM will come up with a correct and helpful answer. We compared 3 LLMs, GPT-4, GPT 3.5, and Instruct GPT, which is not really optimized for conversations. And we had 25 participants with various backgrounds, from maths undergraduates to fields medalists. And we tested on Proof Wiki problems from 6 categories, from senior undergraduate to graduate level problems. And we were interested in the following questions. How important is correctness versus helpfulness to people? What makes people stop interacting with LLMs? And what do people use LLMs for, and how does this evolve? After our human mathematicians were done with interacting with the model, we asked them to rate the responses of the LLM for 1, helpfulness, so from actively harmful to definitely helpful, and 2, for correctness, so from nonsensical to completely correct. We recorded 261 interactions in total, and so what did we find? Here we plot correctness against helpfulness as perceived by our human participants, mathematicians. So higher is better, and each dot is a score of a single human interaction. So we have correctness and we have helpfulness. And we add a slight jitter for visual ease, because the points will obviously overlap. So that's why they're slightly out of sync. And we found that correctness and helpfulness indeed correlate. But interestingly, we observed cases where the perceived helpfulness and correctness of a generation were also diverging. We would kind of expect this cluster up here when the answers are correct and helpful, and we would also expect a cluster down here when the answers were totally incorrect and totally unhelpful. However, even if the answers are somewhat incorrect, our mathematicians may still find them helpful. And this is the inspiration cluster that we are terming up here. Or they could be almost entirely correct, but really unhelpful. And so we have this dull cluster here. So this last one often happens when LLM gives an overly verbose answer. Next, we looked at when do people stop interacting with the model. We were interested to see how our correctness and helpfulness of the model's answer related to when people actually stopped interacting with the model. So here, the size of the bubble, the size of these bubbles, indicates the number of that particular correctness, helpfulness pair. And the opacity indicates the proportion of stopping steps. So the darker the bubble, the more stopping steps out of all steps are in that bubble. So we can see that participants kept on going until they were satisfied. This is when both ratings are higher than 4. So the model could clearly solve the problem and assist the human. Or participants seem to stop early, frustrated. This is when both ratings are lower than 2, so the model completely failed to prove or to give any further assistance or any useful mathematical knowledge. This is where people received the response from the model, tried to correct it, and the response came back still in this frustration cluster. But that's not really surprising, because if an LLM doesn't understand the problem, more interaction with it, we can't expect it that it's going to pick it up while we're interacting with it more. Okay, next we looked at how people interact with chatbots. So you will see here that these are sort of different types of interactions of what people were doing with an LLM. And here the blue step, so step 0, is the first interaction. So it's just a statement of the problem and no response from the model yet. And so what do people actually do first? And the orange step here, so this is, we call it step 1, is the second interaction, because it's after one response from the model. So what do people do next? And then we found that people in their first interaction mostly use the model to ask it for definitions. You will see, so that's the blue ones. You see these are not big. So ask definition or copy paste the problem in order to see what the model does. In contrast, in the second interaction, when the model had already provided some output, people opted to using the model more for general maths questions or asking how to proceed or how it's doing something. So basically clarifying questions. So this too is not particularly surprising because definition retrieval works extremely well. So this is one of the areas that LLMs are particularly good at. On the other hand, over-reliance on memorization makes the model fail at questions that look similar to some other famous questions, but different. So it's erroneous. Okay, so we systemized our findings into recommendations for mathematicians and for developers of LLMs. So for mathematicians, be careful because LLMs are really good at coming up with convincing yet faulty answers, especially when you can't verify the solution easily. And we found cases where an LLM answer was wrong, but the mathematician was completely convinced that this is entirely correct. And also, be discerning at how what you're choosing an LLM to help you with. So currently, and this changes extremely rapidly, it's really bad at doing heavy algebra, for example. Okay, for developers of LLMs, we say that humans care mostly about how certain the model is about its answer and the reasons for the answer, and that the answers are actually brief. We also carried out a qualitative study with 3 experts conducting case studies with GPT-4 from particular perspectives. And you can go to the appendix of the paper here, of the paper here. You can scan it and go to the appendix and you will find how Tim Gowers is extremely patient with the GPT-4 over 30 pages. And this really is a thing that he said to LLM. Okay. So, our study is only a first step towards making LLMs our collaborators. It gives us an insight into how human mathematicians interact with these systems and what LLMs are good at and bad at. It gives us a glimpse into the need for new ways of evaluating success, like our work here, which is looking at interactivity. So, my first take-home message is that AI systems can provide a collaborative environment for mathematical exploration. But there is much work that still needs doing, especially in enabling humans to collaborate creatively with AI. And I will return to this later. Okay, so now that we know what language models can and cannot do in natural language, let's look at how to make mathematical reasoning automated, rigorous, and valid. So mathematicians have recorded their discoveries over centuries in books, journals, MathWiki, math blogs, stock exchange, stack exchange even. No, not financiers. And in comparison, the proportion of maths that is formalized for machine learning in, say, Lean, Isabelle, Rock, Mizar is tiny. And similar is true for other areas too. For example, the domain knowledge in medicine or biology or other fields is in journals and ontologies and knowledge graphs. The size of informal human knowledge is vast. We wanted to capitalize on this, on all of the human formal and informal knowledge in order to make AI reasoners capable of such human-level reasoning. And LLMs such as ChatGPT and Gemini nowadays are really enabling us to access this vast resource of digitized human knowledge and put it in the format that is that reasoning machines can actually use. So by integrating informal human knowledge, we can enhance the problem-solving capabilities, but also the human-like nature of AI solutions. So in my group, we decided to do just that. We built a method called autoformalization that utilizes the power of LLMs to formalize human informal maths. LLMs like ChatGPT, Llama, Gemini are very good at generative modeling of distribution of sentences. And they need very little prompting to do in-domain reasoning. So the same actually applies then for maths domain, not just for natural language sentences. But autoformalization is not an easy task because much information in informal proofs is missing, as we also saw by the invisibility that invisible maths that Emily was talking about. And we lack data sets to train machine learning models, and there's only a small amount of aligned pairs of informal and formal statements which are used to train LLMs. So we took informal statements from digitized repositories and used our method of autoformalization to translate them into formal statements of Lean and Isabel. We also took existing formal statements in formal libraries like MathLib and Archive of Formal Proof and informalized them into natural language. And this is a far easier task. And this way we could construct data sets of aligned pairs of informal and formal statements for training and improving the translator. And here is what we found. After autoformalizing with LLMs, Palm, and Codex around 4,000 problems from the math dataset and the mini F2F benchmark, these are sort of high school competition and maths Olympiad level problems in algebra and number theory, like this one here. Over 86% of them were syntactically correct. We randomly picked 150 of these Isabel formalizations and manually inspected them. And we found that 38 had perfect formalization, a success rate of over 25%. And most of the mistakes could be caught by some proof assistant. So let us look a bit more closely into a couple of examples. So in this first one, the model could formalize that there is no function f into assuming there's such a function, prove false. And the model also understood what it means to into itself. And in this second example, we have a secondary school maths problem that is completely out of distribution. So the model has never seen this type of problem, and the model did it perfectly. So our findings show that LLMs can formalize despite little data and little pre-training corpus, and that LLMs are capable of auto-formalizing completely out-of-domain problems. Now, how can we put this auto-formalization into use? So far, we've seen auto-formalizing statements, but can we do so to proofs as well? Can we improve neural reasoners with auto-formalization? So let me give you an example. Here's a problem that machines are not good at solving, and in this case, because they may not know about the lemma, about the greatest common divisor, so GCD, and least common multiplier, LCM. But mathematicians have recorded this solution, for example, on Stack Exchange. And we built an architecture where we use an LLM and auto-formalization to harvest these informal human solutions. And here's one such human solution of our problem harvested by an LLM. And the first step in this process is for take a human proof and put it into an informal proof draft. So we can use a human-supplied informal solution, or we also use LLMs to generate new informal proof drafts.
Why not, like,
From a human proof corpus like Stack Exchange. We then ask an LLM to auto-formalize them into formal proof sketches. And these sketches, they encapsulate a high-level idea of the proof that comes from the informal human proof. We then copy segments of the drafts as inline comments into the formal sketches to create a good alignment between formal and an informal part. But there are still gaps that are left in there. And here we use a formal theorem prover to close those gaps. And in this case, we used our in-house prover, Isabel, because we have expertise, in-house expertise in it. So we pass these sketches to a machine reasoner who can check the steps and solve any gaps that remain in the sketches. And we call this step proof. So here's a high-level overview of the architecture and the process draft, sketch, and proof. So draft, we use either humans or LLMs. In our case, we used humans as well as Codex and Minerva to draft informal proofs. Then sketch to transform informal drafts into formal sketches, and we used LLM Codex in order for this auto-formalization. Now notice how I used an LLM twice. In the first step, I used it to harvest the informal human proofs, and in this second step, I'm using it for a different purpose in order to auto-formalize drafts into sketches. And finally, proof. So we use an off-the-shelf reasoner, here Isabel, to verify the steps and close the gaps in the proof sketch. So we have draft, which is human knowledge, sketch, which is neural methods, and we have proof, which is symbolic methods. It turns out that this approach vastly improves the reasoner's power while producing proofs that are much, much more aligned with human solutions. So now Math Olympiad problems can be solved by a machine that before they could not be. And our method of prompting LLMs and interleaving comments and in the proof segments is now the standard for proof auto-formalization. So my second take-home message is that we can use methods like our auto-formalization or draft, sketch, and proof to capitalize on human domain knowledge and improve the reasoner's capabilities in terms of rigor and validity. There's still much to do, and since these were only simple maths problems, and we lack good data sets of conjectures, but it does pave some of the way towards a rigorous AI mathematician. Finally, to complete the loop, we need conjectures. Not just any conjectures, but good conjectures that will enable my AI reasoner to get better at solving our target problems and provide human mathematicians with relevant and interesting insights on the way to solving a problem. This is our current work. So remember our vision for a human mathematician from the start of this talk? Well, so far we've implemented this self-improving loop, conjecture-prover loop, without explicit human input and collaboration, and I'll return to this human part in a minute. So the conjecturer here generates new conjectures, And these conjectures are then the prover tries to prove here. And then we evaluate these provers that is trying to prove these new conjectures, and we pick the best conjectures and use these to update the conjecturer for, and the prover, in fact, for the next round of generation. Now, currently, we evaluate success by testing the prover on a fixed target set of theorems to see if it can now, whilst going through one of these loops, it can prove more target theorems than before. But of course, there could be other ways of selecting good conjectures. So let me see what you think. So what would you consider to be a good conjecturer reward function? That the generated conjectures are diverse, that the generated conjectures improve the prover's power by enabling it to prove more theorems. The generated conjectures are elegant and understandable to humans. Or perhaps you have a different suggestion. Let me see. I can see hands up already. Please.
Conjecturing, you're going to say all of the above.
Very good. But do you any other thoughts? What constitute a good conjecture?
I think you want something surprising.
Ah, very good. That's on my list too. Very good. Yes. Anything else? Yes.
I think looking at the notion of intuition and its relation to counterintuition.
Okay. So like counterexamples, counterintuition. Yeah. Okay. Yeah. Anybody else? Yes.
Interesting.
Interesting. Yes. Interestingness. In fact, we actually did a little study where we went to the Maths Olympiad and asked the participants, gave them theorems and asked them to evaluate how interesting those theorems were. So according to very many different criteria. So, yes.
Go
ahead.
It should be either easier to prove or easier to disprove than whatever the original theorem is.
Okay, that's a good one. Yeah. Anything else? Yes.
Just this minor shift in terminology, but I heard the expression of beautifulness.
Beautiful, yes. Yes. Does that mean that it's elegant, beautiful, simple, complex?
I have no idea, but talking with many math enthusiastic people, everyone has their very personal beauty metric that is interesting to
We would
discover.
need to do a cognitive evaluation study to formalize the notion of beauty, right? Anything else? Yes.
How much information does it pack in some notion of information?
Very good. Yes, yes. We were also thinking of things like how useful it is. Does it help to prove just one other theorem, or does it help to prove lots of different theorems? For example, that was also one of the things that we looked at. We were also looking at things like how surprising it is, right? Anyway, thank you for that. Interesting suggestions, and our current approach in our current work, we are prioritizing prover accuracy. So the conjecture helps training the prover to prove more theorems. But in the future, we aim to balance all three, and in fact, we will also consider your suggestions. So let me give you the intuition of how we currently select our conjectures. The main goal of our training pipeline is to fill in the gap between the two sets of theorems. So we have our initial seed of theorems. These are the easy ones that the base prover can already prove. Then we have these ones, which are our target set, and these are the harder problems that the base prover can't prove yet. So what we want to do is to generate new conjectures that gradually bridge this space between between the easy problems and the hard problems. So that's the hard ones are in our target. So the further we go from the seed, the harder the problems for the prover, and the closer to the target set are the generated conjectures. So this way, we are making the training set much richer and more helpful for learning. So to select the initial seed, to select the initial target set, we run a prover on a set of around 2,000 problems for which we do have access to their proofs. And if you're interested, this was from the Numina dataset. For the initial seed, we randomly select 16 statement proof pairs for which the prover was able to find a proof in 8 out of 16 attempts. And for the target set, we select the subset of statement proof pairs for which the prover was unable to find a proof after 16 attempts. Then the process goes like this. So the conjecturer is given the initial seed statements. It then generates a new set of conjectures, one for each seed, one set for each seed. Then we train the prover. We trained n different versions of prover, however number of seeds we had, so however many sets of conjectures we have. We then evaluate each one of these different provers and to see how well they do on the target set. And then we select the conjectures from the prover that did the best on the target set, and we use this as the new seed for the next iteration for the conjecturer. And we also update the base prover with these helpful conjectures. So the base prover now is better and hopefully able to prove more target theorems, right?
The conjecture is first proven to be true?
Pardon?
The conjecture is first proven to be true?
So this is exactly what happens, is that we try a prover on each conjecture set, and then some of them will be true, or for some of them our prover will find the proof, and for some it won't. And for the ones that it does find proofs, then we are selecting those as good conjectures that are close to the target set. So yeah.
How do you know it's close to the target?
Okay, so that's a very technical question. So we're looking at the distance in the hidden space of the last layer of the neural prover.
Oh, a latent space.
Yes, in the latent space, yes, of the neural.
But that might not be true in terms of actual formal mathematical space.
Yes, quite possible. Yeah, you're right. And then, so once we've done this for the first iteration, then we repeat the loop. So we have new seeds, new generated conjectures, new best conjectures, new seed again, and in this way, the conjecturer progressively generates statements that move closer to the target set. And in the process, it improves the prover with respect to this target set of theorems. So now that we have the intuition of what we're trying to achieve, here's the method that we implemented to achieve this. Okay, so step one. In the first step of this loop, we are generating conjectures from seeds. So for each seed, we generate 64 conjectures. Okay, so we have these n seeds, so n sets of newly generated conjectures. In the second step, we are training n different versions of a prover, so one for each set of conjectures per seed, right? In each version, we are using a version of the reinforcement learning algorithm called GRPO. And at the end of this step, we obtain n different prover models. Okay, in the third step of this loop, we are evaluating now all of these n different prover models. And we are running it on the target set to see, after that it's being fine-tuned with these new conjectures, whether it's doing better. And at the end of this step, we obtain n different evaluations, one for each instance of the prover. In the fourth step, we are selecting best conjectures, and these are the ones that led to the largest increase in performance of the prover model. And at the end of this step, we end up with n selected conjectures, and these are going to be our next new seed for the next iteration of the loop. And finally, we update the base prover with these good conjectures that we're using as a next seed. And so now the prover is actually better able well, the hope is that it's better able to prove or tackle the target set of theorems. So, okay, so let me give you an idea of what the seed and target theorems look like and what the conjectures that are generated look like. So here's a seed and a target theorem, and remember, the seed could be proved, but the target could not. So we used an LLM pre-trained on maths data and fine-tuned to produce lean proofs. And here is a generated conjecture. So you can see that it looks quite similar to the seed theorem. And we also used an LLM for a conjecture too, and the same LLM pre-trained on maths data. So remember, this is a generative model. So we first train it on triples of two statements that have a similar proof and a proof of the first. So now when we need to generate a new statement, we can give it a seed theorem and a seed proof, and it will generate a similar statement. Okay, so, right, here are some very, very, very preliminary results, hot off the press from last night. Thank you very much. Marco was running this for us. He was doing most of this implementation. Thank you, Albert, at the back there, and thank you, Wenda. This is our collaborative project here. So the goal is to generate conjectures that help the prover improve and solve more problems. Initially, the prover could not prove any of the target theorems, although you might wonder why there is a 2 here in the iteration 0. It's just because there's randomness in the system. So on the one run, it will give us 0 proofs in 16 attempts, and on another run, it might give us, well, in this case, 2. Okay, so we did that, and we tried it actually on 49. We had 49 target theorems. And we found that after one iteration of this loop, the prover could actually prove 10% more theorems. And after 2 iterations, even more. Now, this gives us hope that not only the conjecture is generating new conjectures, but it's also generating helpful conjectures. And so watch this space as we scale this up to many more iterations and see what happens then. So yeah, literally last night. It's a good job that it came up with a good result, as we hoped. And yes, thank you, Marco. Thank you, Albert. Thank you, Wenda. All right. So far, our pipeline is automating the use of conjecture and prover in this self-improving loop. But what about the human? And that is our future work. So we want to enable a human to take advantage of this reasoning pipeline so that they can explore their own conjectures, or that they can collaborate with an AI reasoning system to help them prove theorems. We see different opportunities for the human to have input and to interact with this AI mathematician. And so they could be submitting their own conjectures to be proved and receive feedback. They could be scoring how good AI-generated conjectures are, or they could be setting what the target theorems should be, or even check that an LLM isn't behaving in some kind of a misleading way. This is where we are going next, and this is our vision for a true human-AI collaboration. So my third take-home message is automated conjectures are beginning to generate useful conjectures, and in collaboration with the human, we hope that they will lead to new insights. So in conclusion, building an AI-human collaborative mathematician capable of making new discoveries requires a multifaceted approach. Throughout our research, today I focused on 3 key aspects. So we have collaboration, rigor and validity, and conjectures. And together, these advancements will play a crucial role in paving the way to discovery. However, much remains to be done, and before we have any hope to make meaningful discoveries. We are improving our neural reasoner by reinforcement learning. We are improving conjecture to generate interesting and novel conjectures. We are building an easy and true collaborative environment between an AI and a human. And there are many challenges facing us. First, data scarcity for cutting-edge maths. We have a lot of informal data, much less formal data, and almost no informal, formal paired data for conjecturing. And the mini F to F benchmark is largely beaten by alpha proof. So we need more, harder, and interesting data sets for training and evaluating. Second, how do we prevent proof hallucinations when AI gets creative? And third, how do we ensure that AI speaks the language of human intuition? I invite you, the exciting bit is that these challenges are giving us or presenting us with an opportunity, and everybody in this room could help solve us these problems today. So I invite you to collaborate on data sets and benchmarks, and to contribute to interactive AI maths platforms. And you can access some of this down here. And let's shape the future of mathematics together. Mathematics remains humanity's most infinite frontier. With AI, we are not just solving problems, we are expanding how we explore. And as we close, I'm reminded of Hilbert's conviction, we must know. Today I say, we will discover together. Thank you.
Okay, so we have plenty of time for discussion and questions. Let's start.
In the first bit, when you were talking about how you had to be careful about the output because it might be like convincing but wrong.
Yeah.
In terms of actually sort of using that conjecturing capability in the real world, where you've got expert mathematicians collaborating with like a hypothetical, more powerful machine learning model, what are your thoughts on how we can get around that issue of these LLM-based systems producing very convincing output that's completely sort of indifferent to truth and accuracy? What are your thoughts?
You're asking me how am I proposing to solve proof hallucinations?
No. I don't.
I would be a very rich woman if I solved that.
But the breathtaking confidence.
Yes.
How do you?
I don't mean necessarily in terms of the output, right? Because that's a difficult problem. I mean, do you have any thoughts on how we can get around that in terms of like the collaboration, the human aspect?
Oh, I see. So you're asking whether, if I understand correctly, is whether something within the interaction can help guard against these kinds of proof hallucinations, or for spotting them sooner, or things like that.
Yeah, like if we assume that that's just a factor of these systems. Yeah.
Well, I think that this quote from Tim, 6 does not equal 7, was one of those examples, right? Where you have to go back and prompt the LLM in order to fix the error that it made, because the human mathematician found spotted the error, which was an obvious one, but of course there are much more complex things that lead you to believe that it's true, but it actually isn't. So I think that as we improve these environments where we have the back end with theorem provers or formal systems checking the steps, and as we enable an easy collaboration and interaction between a human and an LLM, we're going to at least be able to with guidance, guide the LLM so that they're not producing these, or at least that they're avoiding proof hallucinations. But I think that actually there needs to be something much more methodological and foundational that needs to be figured out about how and why these hallucinations are happening and how we can prevent them.
Thank you.
Yes, you and then
Ferenc?
So I was wondering for the conjecture generation.
Yeah.
Another thing you could potentially do in the formal setting is explore different proofs of theorems that are known, that are in your database. So trying to kind of explore a diverse range of different ways of proving the same thing. Do you think that would have potentially similar value in terms of giving your agent more data to then prove the target?
Yes, definitely. In fact, I think that we have even shown that the diversity benefits this whole process. So yes, definitely. And in fact, this is also one of the criteria, or that we might use. We haven't used it yet because we're only just starting, but as one of the criteria for selecting good conjectures, you know, how diverse, how different they are from the previous ones.
Sorry if I may rephrase. So I'm saying, like, for the same conjecture, let's say that it is...
Oh, you have 3 proofs or something, yeah?
3 different proofs. And
yeah.
It's like the...
Yes, yes. And in fact, we do this in some way, because with the prover is running 16 attempts, let's say, for each conjecture, and each one might come up with a different proof. I didn't show the results here, but there are some, for example, that in 16 attempts it might find 16 different proofs, and in order to pass here, it just needed to find 1. But yeah, definitely, I definitely think that this would help. And it will become more creative as well, because you have more options of where to explore, yeah. And as these environments are starting to give you sort of their reasoning process of how they came up with the answer they gave you, then you can also see and tackle into that, or tap into that to use it when you're prompting it for new conjectures or giving it your own, because it might give you an inspiration, right? That's the idea, I think. But we'll see. We're working on it. Hello.
My question for AI. If you can generate conjectures, probably this system can generate the mentioned math-Olympiad problems.
It can generate what?
Math-Olympiad problems.
Math-Olympiad problems, yes.
Because many conjectures are good as such math-Olympiad problems.
Yes.
Is it possible?
Yes, we've done this. Yeah, we've trained with auto formalization. We've trained stuff that the prover that was able to prove a math Olympiad problem.
Proof, but generate new.
Oh, a generate new problem. Ah, that's a much more challenging proposition. Yes, that would be the hope.
Yeah,
I mean, that's why I'm saying.
Conjectures. Many conjectures are very good.
Yes.
Yeah.
That's our vision.
Yeah.
Just clarify a question about this part where you talked about the conjecture generating stuff. Also maybe related to the previous question.
Yeah.
So when the whole thing is just a neural theorem prover. You don't actually use a formal theorem prover in this case. Like you could generate a conjecture and try to prove it with a formal theorem prover or a proof assistant, and then give the signal back to the conjecture generator to generate a new conjecture.
Yes. Yes. Except that it's fine-tuned to produce lean proofs, so I guess it's seen lean proofs, but it's not, the lean is not standing behind it to check the statements. You're right. Yes.
Potentially it could, or why would you not?
You could, yes, you could. And in fact, with the draft, sketch, and proof type method, we should be closing gaps, and yeah.
So just following up on that, you don't make use of the failure of the lean proofs in any construction.
No, we don't do that now. No, we don't do that currently. But I think that that's another avenue of work because failed proofs are extremely useful because they show you where things go wrong, and they might suggest you what new extra conjecture you might need. And in fact, there was work done on this before on how to generate new lemmas and things like that. So up in Edinburgh with Alan Bundy, so in his group, yeah.
Are you thinking about the counterexample based generation?
Yes, or counterexample, exactly. Counterexample, failed proof, all of those are really useful sources for, I guess, diversity and inspiration for conjecturing, yeah. I don't know, Marco, do you have anything to add, or Wenda or Albert, since we're working on this together? I put you on the spot, sorry.
Yeah, you can actually map them during the break or map material.
Yeah.
Just to, so you?
No, you.
Okay. Just I wanted to come back to this thing about using the latent space metric as resistance and proofs.
Yes.
Because it's really interesting. But what I would worry is that latent space embedding is completely built on how you've trained it.
Yes.
And that where interesting proofs will come is sort of in the stuff that you've not already trained. So there could be something which is in, if you like, a different direction or embedding, because you put a metric based on sort of the successes of the past. So it's not, well, if you wanted a whole new thing, it doesn't know about that new thing.
Yeah.
It won't have a proximity in the latent space where that metric is induced. And I've just got one sort of technical question. Was it cosine similarity you used?
Marco, what are we using? Cosine similarity?
Yes.
Yes. On the last.
Dimensionality is high.
Yeah. Yes. But the point really is not so much. So we are using this in order to generate similar conjectures to the seed. Let's see here, to the seeds. So the whole point is not so much that they should be super different to what the initial seed is. The point is that this is sort of an evolutionary process, that as you go through the iterations, all of these seeds sort of move closer and closer to the target. So it's not one metric that is going to now enable you to now be very close to the target set. It's like a small similarity that then it gets reinforced in this loop which is run several times. So that's the idea, that's the whole point. So that metric is actually not super, I mean, it's important, but you could have used a different metric too, right? Yes, Wenda.
Yeah, I would say so, because here we are considering being able to prove more theorem could be a useful signal to reinforce our conjecture, but that does not rule out the possibility of including other metrics in the future. For example, personally, I really like maybe a good conjecture is the one that connects different branches of mathematics, or maybe more interesting. But then again, so how can we measure interestingness? I think it's a problem. But right now, the computationally feasible metric we are having is just the kind of most straightforward metric for us is just to be able to prove more theorems. But then in the future, we will certainly explore other metrics to reinforce the conjecture.
Yeah.
Sometimes like library learning, I think there's a lot of work on. There's a work on called Dream Coder, which I really appreciate that. So it's a library learning. So how can we kind of learn a super express library that kind of to express more things? It's really a kind of idea of like intelligence is compression, and with library learning, okay, can we learn something more abstract and more compressed?
Yeah, and that's where the counterexamples and failed proofs will come handy.
Yeah, certainly.
Yeah. Mario.
Yeah. So I mean, I guess I was thinking about this 6 9 = 7 quote, and it sort of has to do with sort of incorrigibility, where like these language models, like when you do, I don't know, RLHF on them, somehow they learn to be more obsequious and say sorry more, but they don't really learn to say something different the next time. And sort of when you have these sort of human conversations, really what you're trying to do is say try a different tack, and then they just don't, right? And do you know whether like this is? I mean, it's possible this is just not a question to ask you, and I should ask like DeepMind or whoever is actually training this. But like, is there something that can be done in order to sort of, move these these models more in the direction of like being able to recognize when they're being asked to do something different and like explore a different part of the space?
I think that's what we were trying to evaluate or get a handle on with this, evaluating the interaction between the human and the LLM. Now, we weren't developing or fine-tuning or improving the LLM. We just were trying to see what impacts the interaction and how it evolves, and when do people give up or when do people keep going. So I don't know, we noticed that when humans were interacting, maybe Tim can say, like, he was our guinea pig, one of them, and Wenda was also one of them. So, like, when we noticed that they were prompting the LLM in a way that would go in the direction that they had the intuition of that it should be going, right? And then I don't know how successful that was, but considering that we have if you remember, we have this cluster. Let me just find it very quickly. We have this cluster here. It's either that it didn't work at all, so people gave up, or actually when they were steering it, it was going in the right direction, and they kept on going until they were satisfied with the answer, and that's the satisfaction cluster. So I don't know. We didn't really look more deeply than that, but I suspect that there are ways that interaction will enable a better or worse steering of the reasoning process from the LLM.
Did you hear a difference in the satisfaction cluster between the ones that sort of basically got it right, like all along, like they were basically there and then they just got it, or the ones which like they were significantly wrong but they could be steered towards being correct and then actually made it?
I don't know. Like, Tim, do you remember? Or Wenda, do you remember?
My memory of these things, usually either with one or two prompts you get all the way,
Everything,
or you
yes.
just get into a boring thing that goes on for ages.
Yeah. So, yeah. But we're not developers of LLMs, but yeah, we want to see how the interaction is going to steer it. Yeah.
Okay, I'll end it with one last question, and then we need to take a break. Can you postpone the question to break? Yeah. So supposing now you're advising, maybe Lena wants to become a mathematician, and you're trying to tell her this is how the future of mathematics is going to be. So what is the division of intellectual labor between the mathematician and the machine?
Interesting view. I wasn't even thinking of it. I always thought of it, it's a collaboration. So they're both actually inventing and contributing to the solution. So a machine might be contributing by inspiring a human. A human might be contributing by giving a creative solution, and machine trying it out and testing it and fixing it or whatever. So I really think of it as a true collaboration.
I could imagine that the future might be a bunch of people in deep mine sipping their margaritas while the machine is
You mean complete automation? No, I never.
Publishing papers.
Yeah.
So
When are you asking this question?
So what?
When are you asking?
Say in 5-10 years. So what does a kind of future mathematician have to
No, I
brace
don't.
themselves
I don't want to. I don't want to scare anybody. Most of the people in here are mathematicians, so let me say this. We, as AI computer scientists, are building machines that collaborate with us, not replace us. So, at least in our work, we're doing that, and I really see it as a true collaboration. So it's not that deep mind people are going to sit back and watch this world get around. No, I think it'll be an interaction. And then that's why we also design these environments to test how the interaction works and so on. Yeah, but yeah, true collaboration, I think.
Let's hope it goes that way.
Yes.
Thanks a lot, Ricky.
Okay.